Okay, today I thought that we would try something a little bit different. Let's go back to the idea of the relativistic projectile, but let's look at it in the case of not a uniform gravitational field, but rather something like a rocket or some sort of ballistic projectile way out in space, no gravity around, flat space-time, but it is going to be subjected to a constant force, at least in a particular frame. And so it will gradually speed up faster and faster and faster. We want to know some of the kinematics relativistically. So as always in relativity, we got to be very careful what frames we're talking about. We might worry a little bit about special relativity not being allowed to be used if we have accelerating frames of reference. Sorta, kinda, it's actually quite okay to use special relativity if you're sitting in an inertial frame and you're talking about what's happening in an accelerating frame, or you're watching an accelerating frame from your inertial perspective. That's all okay. So what I want to do here is I want to actually look at this rocket. Let's say the mass is m. So this is not something that's exhausting its mass. We're not looking at the relativistic rocket yet. It's something with a constant mass. Just somehow there is a force that's acting on it, and that force is constant in the inertial frame that I'm starting in. I don't know if this is Earth or I'm just sort of floating out there while it rockets by or something, but this force is the force that's measured in my frame, the force I'm seeing on the rocket. Maybe I'm the one pushing on the rocket, at least initially. Of course, I'd have to keep up with it, so I guess that's not really the best example, but there's some sort of force that is constantly pushing it in the inertial frame. Now, we want to find the speed of this rocket, its position, and its acceleration in my inertial frame, and then also calculate the same quantities, not in terms of the coordinate time t, but in terms of the proper time tau. Notice, I'm not saying these are being calculated in the rocket's frame. After all, the rocket in its own frame would have zero velocity. But what I am saying is I want to calculate what these are, both in terms of coordinate time t, that's my inertial clock, and also in terms of tau, this proper time on the rocket. Okay, so how are we going to do that? Let's go to the inertial frame. I'm going to start working in the inertial frame that's watching this thing accelerate. And we know Newton's second law has to hold. I have to write it in its general form. I can't really write it as ma because that's not really appropriate relativistically. But it is true that the force will be the rate of change of its relativistic momentum. And since I'm doing this in the inertial frame, I'm taking time derivatives with respect to coordinate time t. Okay, let's also remember that the relativistic momentum is written in terms of the velocity in this frame as this Lorentz factor gamma times the mass times its velocity. And as a reminder, there's a couple symbols that are commonly used in relativity just to keep the notation simple. Beta is going to be sort of the dimensionless speed as a function of the fraction of the speed of light, and gamma, that Lorentz factor that gives us things like time dilation and length contraction, depends on v in this funky way. Now here, of course, we can see that these both will change with time because beta depends on v and gamma depends on beta. So we could imagine doing some sort of product rule here. We don't need to, though, because we are assuming that this f is actually a constant, so I can just directly integrate this equation. I'm also going to pull the m out. I'm actually going to divide both sides by m because we know that the mass is constant here. We're not really dealing with thrust or relativistic rocket yet. Okay, so what does that mean? We'll have basically f over m dt is d of gamma v. I'm going to define this thing, f over m, as g. And I want to be a little careful with what this g means. I'm thinking about it kind of like an acceleration. I mean, it's a force per unit mass. That makes sense. But we should be a little careful. This is not necessarily the acceleration of the rocket. It's just its force divided by its mass. In Newtonian sense, it would be g. It would be the relativistic, it would be the non-relativistic acceleration, like a gravitational field. Here, g is not quite playing that role, but it is something with units of acceleration, so I'll just define that to be g, and we'll see that this could kind of work in the case of launching straight up in a large uniform gravitational field. That works well too. And of course, I'm going to start everything at time 0. And I'm also going to imagine that the rocket starts at rest. So v, which is what I'm really integrating here, is going to start at 0, and then I'm integrating up to gamma times v. So we'll get no constants of integration on either side, and I'll just have gamma times v. And just as a reminder of what that writes out, that's not so bad. Okay, that immediately gives me my first answer here. Maybe I'll write it in blue over here, that the velocity as a function of coordinate time, just by, remember there's a v inside this beta, swapping some things around, is going to be gt over the square root of 1 minus gt over c quantity squared. So that's just a little bit of fast algebra there. And we can see what happens. Okay, when t equals 0, it's at rest. Good, because that was the assumption right here. We can also see that as time approaches infinity, the numerator keeps growing and growing. You might say, oh, it's going to go faster and faster, maybe exceed the speed of light. Nope, that won't be the case because the denominator fixes that. We can see that as, we can also see I made a little sign error there. Sorry, it's a plus sign. When t goes to infinity, this 1 basically becomes negligible, and then the square root of this thing cancels the gt, and we just end up with c. So indeed, as we approach infinite time in the future, this thing will accelerate, but it accelerates up to some maximum speed, which is the speed of light. So that's not too surprising. It just sort of starts at 0 and then gradually accelerates asymptotically towards the speed of light. If we wanted to include maybe a little graph of what that looks like here. So here's coordinate time and the speed of the rocket. It starts at rest, and then it will asymptote out to the speed of light c. And actually, this initial slope here is g. You can kind of see that by either looking at a small binomial expansion or literally taking the derivative. So its initial acceleration, meaning what you would see in the Newtonian case when v is very small, is indeed the slope of the velocity graph, which is g, but it does sort of asymptote out to the speed of light. Next thing we want is, what is the position as a function of time? All right, well, we're going to have to integrate this v one more time, so that's not too bad. I'm also going to assume that this starts at the origin, whatever x equals 0 is, and we're just doing one-dimensional motion here. So I can write v equals dx dt, separate these out, and then we'll just integrate both sides. So I'm going to have the integral of dx from 0 to x, and on the other side, I'm going to have the integral of v of t dt from time 0 up to time t. But of course, I have a formula now for v. And what do we have? We'll have gt over square root 1 plus gt over c quantity squared dt up to some time t. So we just have to do this integral. Okay, I could be real glib and just say, it's something trivial, but you know, I don't always like doing that. So let's actually do some good integration practice. All right, I see t is my, my variable here. And, well, if I let this whole thing under the square root be, say, something like a u, then the derivative of that would pull down a 2, and I'd end up with this gt stuff times my dt, and I'd be ready to just integrate directly. So I think we'll just do a u substitution here. Let's go ahead and let u equal everything under this square root. Notice that my differential then, I'll pull down a 2, I'll have a gt over c, and I'll have a dt. So that's going to be a nice substitution. My bounds of integration are also going to change. So when t equals 0, u starts at 1. And when t equals t, well, I'll just get 1 plus gt over c quantity squared. And I do like doing my integration, changing variables when I do a definite integral, including the bounds, because why bother going back to the original thing if you're doing a definite integral? There's really no reason to do that. So let's see what we got here. Well, the bottom is root u. That's kind of by design. The gt dt, which is up here, is good to go. I just have to move the c over 2 to the other side, and I'll have a du. Okay, so that's not so bad. Something's weird about the units here. Let me just double check. Oh, of course. These should still be squared because the derivative I took was only of the t, not the g and the c. But hey, that's unit analysis in vivo, so to speak, because I can see I need a distant something that's got units of length, and I had something that was units of speed. U is dimensionless, and that doesn't make any sense. So don't forget that only t is being differentiated here. So I'm actually going to get a c squared over 2g. There we go. One of the g's times the t will be up here, and the rest won't. Okay, that's not too bad. The c squared over 2g, which, by the way, does have correct dimensions of length, comes out to the front. I've got an integral of 1 over square root of u. That's u to the minus 1/2. I do my usual rule of adding 1/2. Adding 1, so I'll have u to the 1/2. And then I divide by 1/2, which is the same thing as multiplying by 2. And we're going from 1 up to this kind of funky combination of units here. Okay, now we just apply the fundamental theorem of calculus. We do get a little bit of simplification here. And I'm going to end up on this side with just x of t. And on the right-hand side, I have a c squared over g. That's got the units I want. And then I've got the square root of this minus the square root of that. But that's just root 1 plus gt over c squared, and then minus 1. Okay, so that's my second bit. That is the position as a function of coordinate time. I'll move it over in just a sec, but look how we do actually have infinite distance that's eventually covered. As t gets larger and larger and larger, the distance grows and grows and grows. It doesn't grow quite like you would expect in the Newtonian case, right? This is not 1/2 at squared, something like that. It's not quadratic. I mean, there's a little quadratic bit here, but it's under a root. So actually, in the long time, it actually grows only linearly with time, because eventually you kind of approach that limiting speed c. You're not accelerating anymore in the inertial frame. All right, so let's see. I've got a bit of room over here. Let's finish this by calculating the acceleration in the inertial frame. So all I got to do there is take a time derivative of my velocity. It's a little strange in relativistic kinematics that you often start with v, even though it's kind of in the middle of position and acceleration. Most of the time in Newtonian physics, you start with the acceleration coming from force, and then you integrate that to get a velocity, and then you integrate that to get a position. And here, we almost always play with v more than a or x, and then we go in either direction from there. Okay, so I got a little bit of room here. Let's go ahead and calculate the acceleration of this rocket in the inertial frame. And I guess I'll go ahead and show the actual work here. I'm going to think of this as a product. So it'll be a time derivative of gt 1 plus gt over c quantity squared to the negative 1/2. I think that'll be kind of the easiest way to work through this. You could do it as a quotient rule also. This g comes to the front of everything, so let's not worry about that. And now I just have a product rule. So let's do first times the derivative of the second, so that'll be a minus 1/2. All of this junk to the minus 3/2. Don't forget the chain rule and do it correctly. So we've got a 2 from the t squared, and then we'll have a gt over c, and those should both be squared. Okay, good. That's not too bad. Then we have plus, well, the derivative of the first is just 1 times all of this junk. Okay, now this can be actually cleaned up a little bit. First of all, this 1/2 and this 2 cancel out. This t and the g's and c's kind of plays nicely. Let me rewrite this a little bit. This last term is 1 plus gt over c quantity squared to the minus 1/2. And then I'll have a minus sign from that guy. I'll have a gt over c quantity squared from all this stuff times 1 plus gt over c quantity squared to the minus 3/2. And then this looks kind of bad, but actually it's not as bad as it looks. So we can actually do a little bit of factoring here. Notice that this is actually the negative 3/2 times a power of 1. Maybe I can show this. What's the best way to show this? Let's factor out this thing to the minus 3/2. And then we'll see what happens here. It's not so bad. Okay, so when I factor that out of here, what do I get? Well, I'm going to get a minus 1/2 plus 3/2, which is 1. So I'm just going to get 1 plus gt over c quantity squared to the 1th power. And then I'm going to subtract off this piece, which is all that's left when I factor that out. But look, this term and this term exactly cancel. And so I'm left with actually a pretty nice looking result, which is g, maybe I'll write it as a fraction, over 1 plus gt over c quantity squared to the 3/2. Okay, a little ugly algebra perhaps, but a nice result in the end. Usually these things turn out to have these sort of algebraic root properties, and it's always going to be that square root that comes in because of these gamma factors that we started with. Here also we can kind of see what happens in the long coordinate time limit. As t approaches infinity, the denominator gets larger and larger, and hence the whole thing gets smaller and smaller. It can't keep on accelerating as it approaches the speed of light, so this does go to 0. And you can see that when t equals 0, the whole denominator is just 1. So my initial acceleration is g. That's why it's kind of convenient over here to think about this slope as being g. That is the Newtonian case. It really does start with an actual acceleration of g. We could have called it maybe a naught or something, but we didn't know at the time what that was going to look like. Okay, so those are all three of those. Let's summarize those here. Okay, so the next thing we want to do is we want to look at these same three kinematical quantities in terms of the proper time on the rocket. Again, I am not calculating these three quantities from the rocket's perspective because in the rocket's frame, it's not moving. It might be accelerating. There is a way of determining acceleration even if you're in your own frame. It's not inertial. But its velocity should be 0. It's trickier there. So we're not talking about these quantities in that frame. I just want to know what they are in terms of this coordinate time. So I can compare how much time has elapsed on the ship versus how much time has elapsed on Earth or my inertial frame. Okay, to do this, we're going to need to rewrite gamma in terms of t, and I mean the coordinate time. And it's convenient to do this right now just because we're going to be not wanting to do tons and tons of algebra later, and it will be sort of nice to have gamma as a function of t directly. So let's just plug in the definitions here. We know that gamma is this messy square root, and I know what v is of t, so I can just plug it all in. I'll go ahead and write this with an exponent here. Sorry, that'll be a minus sign. And of course, it's going to be beta squared. Beta is just v over c. Whew, a lot of exponents there. Okay, we agree that this is v over c, that's beta. We're squaring it, 1 minus that, and it's all to the negative 1/2 power. Let's clean this up a bit. First thing is, let's square this, so that's going to be kind of nicer. We get our gt over c. That quantity shows up quite a bit here. And then kind of unsurprisingly, it looks like this is going to clean up nicely with a common denominator. So let's go ahead and change this first guy into a 1 plus gt over c squared over 1 plus gt over c squared. And then we'll subtract. when I do the subtraction, the quadratic terms actually cancel. And these will be the same thing, so I might as well just write it like this. Carefully, though, maybe I should take my time. So I'll write it out. 1 over 1 plus gt over c, quantity squared, all to the negative 1/2. That actually means this is going to flip up. It's going to be a square root in the numerator. Okay, so that's gamma of t, and it came out kind of nicely, like as I promised. Notice that it does start at 1 because we start at rest, and as t gets larger and larger, it does grow arbitrarily high, which makes sense because you're approaching the speed of light. Now, how are we going to use this gamma to calculate a relationship between the proper time, the time that elapses on the spacecraft, and the coordinate time, the thing that happens back on Earth? Well, we're going to basically use the time dilation formula. Let's see, I think I have enough room here. So let's go ahead and recognize that the amount of time that goes by on the spaceship, and I'll do a little differential version of this right now. Tau is going to be the proper time. It's the time that elapses on the clock on the spacecraft, which is just at rest, at least with respect to the spacecraft. That's going to be related to the coordinate time with a 1 over gamma. And this is the usual time dilation result that says, basically moving clocks run slow. It's not the best way to think about it. Relativity is full of little subtle nuances. You got to be careful. Both clocks are moving with respect to one another. So how do you know? This is the time that elapses on a clock that is on the ship. And then this is the time that goes by on, say, Earth. We're going to divide by gamma, a number bigger than 1, bigger than or equal to 1. So we are expecting less time to go by on the ship than on a clock that stays on Earth. And now, integrating both of these, we'll assume they start at the same time of 0. We have tau being the integral from 0 to t of 1 over gamma, like this. Okay, so this is also a fairly standard integral. I guess I'm just going to kind of cut to the chase. Maybe I'll show one little step here. We'll make a little u sub again. Let's let u equal gt over c. It's a nice little dimensionless number that'll make this look a little more familiar, perhaps. So that du is g over c dt, just to pull the units out. And we'll end up with tau being, well, when I do my dt, I'll get a c over g that comes to the front. That has the right units. And then we'll end up with an integral. Notice it still starts at 0, but it goes to now gt over c. And we'll have a du over root 1 plus u squared. Now, this integral, you could do it with some horrible natural log thing, but this is where hyperbolic trig functions really shine. This actually is the inverse hyperbolic sine function, sinh or arcsinh if you want to call it that. And you can check that, oh yeah, the derivative of this will give you this square root. It kind of looks like sine, right? If this was a minus sign, you'd have the arc sine. It's a plus sign, so you have arcsinh. I'm not going to prove that here, but it's a commonly known thing. In relativity, hyperbolic trig functions show up all the time, and it's baked into the basic structure of relativity. Lorentzian spacetime has this metric that allows for rotations in space, yes, but also boosts that involve hyperbolic rotations. There's a time and space minus sign, basically, that gives rise to these hyperbolic functions. So it does pay to get very comfortable with hyperbolic trig functions. Now, of course, the arcsinh of 0 is 0, so we have our result. Okay, so what does this say? It says that both of these get larger together. The hyperbolic sine function, you can rewrite it in terms of exponentials if you want, but it's essentially going to grow like an exponential. So as t gets larger and larger, tau will also get larger and larger. Sorry, that's an inverse. I should say it the other way around. It goes like a log because we're doing an inverse here. As t gets larger and larger, tau also gets larger and larger, but only logarithmically. And in fact, if you really need it, the inverse hyperbolic sign of some argument can be rewritten in terms of a natural log. Let's see if I can do this from memory. Oh, God. I'll correct it on the screen if I made a mistake here. I'm pretty sure that's right. There might be like a minus sign here, but I think that's right. Anyway, we can see that it sort of grows logarithmically with large times. Okay, this is going to be very nice because now I have a relationship between tau and t directly. And it's really just going to amount to solving for t, plugging into all these, and we're going to get all of our answers for free. So let's bring that over and start doing that. Okay, so I went ahead and just rewrote it in terms of t in terms of tau instead of the other way around, so I don't have an inverse hyperbolic sign anymore. I don't have arc sinh. I've just got sinh. And now we're just going to plug this t into all three of these and see what simplifies out. So it's really just a practice in hyperbolic trigonometry. So let's first find v of tau. Let's see, plugging it in here. Well, the g's will cancel. I'll get something that involves c. That kind of makes sense. So that'll be my unit, c. I'll have a sinh, g tau over c. And then in the denominator, we've got a square root 1 plus. The g and c will cancel the c and g here when I plug it in. So I'm just going to have a sinh squared of g tau over c. And now we want to take advantage of some nice hyperbolic trig identities. First of all, kind of the defining feature is cosh squared minus sinh squared is equal to 1. This is the hyperbolic version of the Pythagorean identity. Instead of a plus sign here, we have a minus sign. So clearly, if I move this over, I'll get 1 plus sinh squared. That's exactly what I have here under a square root. That'll just be cosh, the hyperbolic cosine. And sinh over cosh is tanh. So that's kind of nice. My velocity as a function of the proper time is a hyperbolic tangent. Double checking as always, when tau equals 0, meaning when it starts, tanh of 0 is 0. So I'm going to start at rest as desired. And hyperbolic tangent grows asymptotically to 1. It's not like the inverse tangent function, which grows to pi over 2 at large argument. Instead, this one grows to 1. And basically, it's because these exponentials and sine and cosine kind of both go to the same value. So at very large tau, we do approach c, and that is also kind of what's desired. Next, let's do x. So x of tau. All right, so what do we have here? We've got our thing out front just to give us the right dimensions, and then we have a square root of 1 plus, okay, g over c times t. Again, the c over g cancels, and I have a sinh squared. Well, we've seen what this is. 1 plus sinh squared is cosh squared. It's under a square root, so it's just going to be a cosh. I've been writing x, sorry about that. That's g tau over c. Okay, so this grows like a hyperbolic cosine. Hyperbolic cosine does kind of, it basically looks like an exponential. Of course, it's symmetric on either side. I can draw a little sketch over here of what hyperbolic cosine looks like. It starts at 1, actually, and then it goes sort of exponentially up on either side. So that's cosh. When tau is equal to 0, cosh is 1. 1 minus 1 is 0. So it starts at the origin as promised. And then we're going to have this grow exponentially as we go on further and further. And that kind of makes sense. Finally, we can look at our acceleration as a function of tau. And notice we're again going to have this behavior involving a hyperbolic trig simplification. This time, we've got a sinh squared of gt over c, and then it's to the 3/2 power. Once again, 1 plus sinh squared is cosh squared. Cosh squared to the 3/2 will be cosh cubed in the denominator. And why don't we just wrap it all up by writing that as sech cubed, the hyperbolic secant cubed. By the way, the pronunciation of these is not entirely standardized, but I like cinch, cosh, tanch, seach, and coseach, and I guess the only weird one is cough. I do use a th there. At any rate, this has the same behavior as mentioned before. So seach starts at 1, just like cosh does. So this starts at G, and then it grows. Well, actually, I shouldn't say it grows. This one actually decays. If we look at a graph of seach, it kind of looks like this. It's not a Gaussian, by the way. And of course, cubing, it's not really going to change the general features here. It's not a Gaussian, but it does have Gaussian adjacent pictures to it. So the acceleration does actually drop off with proper time because we already know it's got to go to 0 as you approach the speed of light. Okay, so I think that that's a pretty good place to stop here. We have worked out the speed, the position, and acceleration, both in terms of coordinate time and in terms of proper time for the uniformly, I don't know how to say it really. It's not uniformly accelerated, right? A depends on time, but the constant force application in a special relativity setting. Remember, all that we're saying here is that the momentum is increasing linearly in time. It does not mean that the acceleration is anymore relativistically. And I think in a future video, we'll probably play this forward a little bit more and see how does this affect the motion over great distances. For example, if you want to go to another galaxy, can you do it? Will people die on the way? That's something for another video. All right, we've got our kinematic quantities, QED.